So in today's talk, we're actually going to cover how to automatically discover your data in your data lake, how to categorize that data, and make it immediately available for your analytics. As soon as it's immediately available, we'll also show you how to analyze that data lake using your data warehouse, where you could easily go from gigabytes to exabytes. What are some of the data lake challenges? Really, it deals with the high variety and volumes of data that customers are having come into their system every day. This rate has really grown over years, and it's really different types of data. So it includes things like documents and files. This could be clickstream data, spreadsheets, log data, and various files that you might be getting into your system. It also includes things that would be normally a relational database or an enterprise application. So these come in as records. And then you also have needs to be able to process streaming data. This could be IoT sensors, it could be various IoT streaming data and other streaming data coming into your system. And customers really want to be able to understand how to very quickly ingest this data, discover it, categorize it, understand it, and really curate it to really drive insights very quickly. The other challenge of data lakes is really data lakes are meant to be able to service many different sorts of users. That could be data scientists driving new AI and machine learning algorithms, business users doing quarterly reports and other analytics on your data, analysts, as well as other applications that might need to be able to use your data lake. I want to start off with a customer example, and then we'll dive into a lot of the technical details. FINRA has built a really powerful data lake on AWS. FINRA really services thousands and thousands of really security firms across over 500,000 different brokers, where they're really monitoring investors and markets within the US. And they've built a data lake that's over 20 petabytes of all this trading information and other data sets. And they bring in over 75 billion events per day. And what they've done is they've really enabled their business users, their data scientists, and their data engineers to be able to really stay ahead of folks trying to manipulate the market. And they did that using AWS services and building a data lake. And the way they did that is they really leveraged many of the AWS services that we're going to show today. And you'll notice a lot of these services are really purpose-built. What that means is AWS really builds our services to do a very specific function. We work backwards from the customers to very specific use cases with our analytical and really all of our services that we offer. And it's really across the philosophy of picking the right tool for the right job. So if you have streaming data coming in, the way you ingest streaming data is going to be very different than the way you might be capturing large bulk ingest data sets from satellites and other systems. If we take a look at the purpose-built analytic offerings that Amazon has, here's a small sample of them. If we take a look over on the left-hand side, going through the process of collect, store, and analyze, starting off with Kinesis. Kinesis is built to be able to handle streaming data. That includes being able to very easily capture, store, and analyze the streaming data, as well as populate your data lake that might be in S3. We also have services like Snowball and Snowmobile to be able to capture large amounts of data. On the storage tier, we also have purpose-built tools to be able to store different types of data depending on the type of data that you need to store. So S3 to be able to have large data lakes and file storage, but we also have NoSQL databases and relational databases, graph databases, and being able to provide things like search and text analytics. On the analyze side, we have services such as EMR, which is really the Spark and Hadoop ecosystem as a service. Athena, which allows you to do ad hoc querying across your data on S3. Redshift, which we're going to really dive into very deep during this session, and Redshift Spectrum to be able to have your data warehouse and extend your data warehouse into your data lake on S3. And QuickSight and many, many Amazon AI services. Across the bottom, you'll notice database migration service and Glue. And those are services that really glue these services together or really bridge the gaps between many of these services to be able to move your data around, extract it, transform it, categorize it within your system. If we take a look at a traditional data warehouse and databases and data warehouses in general, you'll notice that many of them are in relational form. What that means is you define a schema up front, and then when you're bringing new data sets into that data warehouse, you have to force fit that schema or force fit that data into that schema. So the schema has to be defined ahead of time. What that means is if you want to bring in new data sets, you have to take a look at that data. You have to understand the schema, fit that schema, create the ETL, and load that data into your data warehouse. Data lakes are quite different in that characteristic. The other aspect is many times data warehouses are really used for operational reporting and ad hoc analysis. If we take a look at how data lakes are really extending data warehouses, we'll notice a couple key facets. The first is you'll notice relational data, but also very non-relational data as well. That could be things like Twitter information, social media information, IoT sensor data, many other data sets that need to be able to come into your system and run analytics on that data. Since there's a very wide variety and velocity of data coming in, data lakes really use something called schema on read. And what that means is rather than force-fitting data into a schema, you save your data first out onto S3 in your data lake, and then you apply a schema when you're reading or analyzing that data. And we're going to show a demonstration of what that looks like here in a moment. And really with data lakes, it's all about being able to handle all these different types of data. It could be raw data as well as curated data, as well as being able to run various analytical tools. So in addition to business intelligence, being able to do real-time analytics, interactive analytics, machine learning on that data. And there's a very strong need to be able to have data warehousing and data lakes complement each other very nicely. If we take a look at what that looks like on AWS, many folks are leveraging data lakes on S3. S3 is a very powerful service to be able to store the content of your data lake. It really provides unmatched durability and availability. 11 nines of durability. What that really means is if you store 10 million objects out into S3, you may on average lose one object in every 10,000 years. And that's assuming it's in one region. We provide many different services to be able to replicate your data across multiple regions, be able to have very strict auditing, object level permissions, so each object within your S3 buckets could have its own authentication authorization on top of that data. So a lot of very advanced features on S3 to be able to store your data. AWS Glue, a serverless service, allows you to really categorize that data very nicely. So you're able to categorize your data on S3 as well as other data sources that we're going to dive into. And it really is talking about being able to run any of these analytic services on top of your data and be able to run that on your data lake and on AWS very easily. So let's dive into a lot of what that looks like. So the data lake architecture, we're really going to focus on some of the core services here. So we're going to show how you could have data in S3 as your data lake, and then leverage the Glue data catalog to be able to categorize and search that data. And then we're going to leverage we're going to leverage Redshift to be able to extend your data warehouse into S3 and analyze that data. Many of these services fall into the serverless analytic category. And what that means is you don't really have to worry about, as a customer, what it takes to provision that service, to make it highly available, to patch the servers. You really focus just on categorizing your data, running your queries, storing your data, and what really matters in your analytical pipeline. It also has a really nice characteristic where you never pay for idle. You only pay as the resources are executing. For example, if you're running Glue ETL, you're only paying as that ETL process is running, and if the process isn't running, there's no charges for that ETL. It automatically scales based on the resources it needs, and its fault tolerance is built into the service. What we're going to dive into in this webinar is the highlighted path here, where we're leveraging Glue to be able to categorize your data on S3, and then Redshift Spectrum to be able to extend your data warehouse into your data lake and analyze your data very effectively. So what is Glue? This is the first service that we're going to go through within the demonstration. Glue provides serverless data cataloging and ETL. And it really is made up of two core components. There's the data catalog and the ETL portion. And you could use these very easily together or separately depending on your use case. The data catalog is a central catalog that really allows you to catalog all your data within S3, your data lakes, and your databases, data warehouses. What it allows you to do within that catalog is then plug in various analytical tools to be able to process that data and drive insights. The ETL portion allows you to very easily write ETL processes either through a wizard, through custom generated code, or various means to be able to execute your ETL to be able to save your data out. And this service is completely serverless, so you don't have to worry about spinning up these servers, managing and patching those services. So if we take a look at the data catalog, one of the key things is the crawlers, being able to have crawlers extract your schema out of your data. And the first example we're going to show is what if I have a whole bunch of different data sets on S3. These different data sets could be in different formats. I might have JSON, CSV, Parquet, other data sets out on my data lake in S3. And the crawlers, what they do is they will automatically identify what the data type is. What is the file type or object type within S3? And then after it does that, it actually examines the data and determines what are the different fields and formats, different fields and data types of that data within the catalog or within that data source. And what that allows it to do is very easily create schema on read definitions of these tables so you could very easily run them against various tools within your data lake. And we're going to execute this live here in a moment when we're going to give a demonstration here shortly. In addition to being able to crawl your different data sources on S3, you could very easily plug it into things like Amazon Redshift to be able to crawl your Redshift tables. You could also plug it into Amazon RDS, be able to crawl MySQL, MariaDB, Postgres, Aurora, as well as self-hosted databases on EC2 for an example. Part of what the crawlers do is they also identify schema similarities. And the way it does that is as it's analyzing the different objects within S3, it's taking a look at what the schema looks like across those objects. And then it allows you to identify if the schemas really are similar schemas and should be treated as one data object with a different choice or different objects in it, or it allows you to create different schemas across your tables. In addition to the built-in classifiers that Glue has that very easily identifies things like CSV, tab delimited, pipe delimited, Parquet, Avro, various data formats, you could write your own custom classifiers. These custom classifiers allow you to create classifiers in Grok or XML and allows you to specify the pattern to be able to process that data out and be able to understand what that data looks like. And these classifiers then get extended and you're able to leverage those in things like Athena and Redshift Spectrum when you're querying your data using the data catalog. Grok is really powerful because in addition to what you could do in regex, there's higher level constructs to be able to do things like IP address, timestamps, message prefixes. So it's a very powerful language to be able to express semi-structured log processing. In addition to the schema detection and file type detection, the crawlers identify the various partitions that you have within S3. Partitioning is a really, really powerful way of separating out your data on S3 to make it so that it's very performant when you query your data. The reason why you want to partition your data many times is if you partition your data and if you're analyzing data using various tools, it could do partition elimination when you're querying your data based on the query parameters. So if you partition your data based on a timestamp and you query for a particular year, it will only scan over the data sets within that year, for example. And the crawlers will automatically identify these partitions and create them within the schema on read table definition in your Glue data catalog. In addition to that, it will version your schema within your catalog, and we're going to demonstrate this here in a moment where over time, either manually or through the crawlers, you could set it up so it'll automatically update your schema as your data changes. And these versionings are kept within the Glue data catalog as well as the most recent version. There's multiple ways to create a table in addition to the crawlers. So you could, in addition to using the crawler, you could manually create the table through the wizard or through the Glue APIs using the create table API call. But you could also do the things like the Hive DDL, or if you're already running a Hive metadata store, we have a set of extraction or migration tools to be able to migrate that Hive metadata store into Glue as well as extract it back out of Glue data catalog into your Hive metastore if you'd like. So that's a little bit about the cataloging within Glue. We're not going to focus on the ETL portion within this webinar, but where we are going to dive into is Redshift. Redshift provides data warehousing on AWS in the cloud, and it's very, very, very fast, and it's constantly getting faster. Many new features every month released within Redshift that improves the performance and adds additional features to our customers that they could leverage. It allows you to very easily bring in open file formats and load those into your Redshift cluster. The Redshift cluster is running, and it's a parallel system where you launch it with a number of nodes, and those nodes store the data locally on the very latest SSDs. The new DC2, for example, has very, very performant SSDs that allows it to load the data. It's very secure. It has many of the different compliances that customers are looking for, ranging from being included in the BAA and various compliance regulations as well. And it's very, very inexpensive to leverage, very easy to scale the data warehouse. One of the examples is the new DC2 of some of the performance increases that we've recently released. So with about the same amount of prices as the DC1, people are getting much greater performance. Here's one customer example, Liberty Mutual, where they had a 9 times reduction of the reporting time it took comparing the DC2 to the DC1. So they just very simply upgraded to the DC2. They saw, for the same price that they were paying, they saw 9 times the performance that they were seeing on the previous version. So, and this is a very common thing. As we're improving the services, you're able to get more and more performant responses. So Redshift loads the data onto the cluster. What Redshift Spectrum really allows you to do is complement that with your data lake. So with Redshift, you have your data on the actual cluster, but then Redshift Spectrum allows you to extend those queries into the S3 data without having to load it on the cluster first. That lets you very easily scale to exabyte range if you'd like, but it also lets you bring in many different types of data formats very, very easily into your data warehouse. It lets you scale compute and storage separately. So if you have very large data sets that are scanned infrequently or are very, very scan heavy, you can push those down to the Redshift Spectrum layer within your clusters. And it's the costing of Redshift Spectrum is based on the amount of data that you scan out of your S3 locations. This is what the architecture looks like. So customers are still leveraging their BI tools or their SQL clients hitting the leader node. So Redshift has a leader node, and that's the central endpoint that many of the different toolings are using in order to talk to Redshift. And when customers are leveraging Redshift Spectrum, they can still leverage that same endpoint. The leader node then goes down to the various compute nodes to be able to delegate the work to be able to execute various queries. If the data has been loaded on the Redshift cluster, it's actually locally on those compute nodes. Or if it's an external schema, which we're going to demonstrate here shortly, it delegates that work down to the Spectrum layer, which we'll talk to S3 to satisfy that request. So here's another diagram of what that looks like. So if a query comes in to be able to count an external table and a group by, it first goes to those essentially those compute nodes. Those compute nodes will delegate down to the Spectrum layer. Each compute node or each slice within the compute node will issue multiple queries to the Spectrum layer. The Spectrum layer will then talk to the S3 to read the various data formats, return the results back up through the leader node, back to the various BI tools or whatever is talking through JDBC, ODBC. A really important aspect about this is customers interacting with Redshift Spectrum are still executing based on the Redshift syntax. So it's very, very easy to issue queries that are spanning both the data that's living on Redshift as well as Redshift Spectrum. And we're going to do a few queries here shortly showing what that looks like. So what does it look like to define that data lake artifact or that Redshift Spectrum external schema within Redshift when you want to execute those queries? Very easily, what you could do is you could create an external schema. You could plug it to the Glue data catalog. And once you do that, it will actually dynamically, when it's issuing the queries, look at that catalog and be able to understand how to read the various partitions and data formats within that catalog. So here's an example flow of what this looks like. And we're going to really demonstrate the bottom flow here, where we have the Glue crawlers that is going to crawl various data sources. Those crawlers are going to populate a set of data catalogs for us. Then we're going to leverage Redshift Spectrum to be able to analyze that data. But that same data set and that same catalog could be used by Amazon EMR to be able to do Spark ML, to be able to run various analytics, as well as Amazon Athena. So that really becomes the central catalog within that data lake as your data is stored on S3. And then folks are interacting through that catalog to understand where to retrieve that data and process it. Nuviad is a really good example of a customer that's leveraging a very similar architecture that we're going to show here, where they're leveraging Amazon S3, Glue, Redshift Spectrum, and Redshift together to be able to really drive their BI tools to be able to see various analytics and reports. And one of the examples that they use this for is really to be able to run against data that's showing up in S3 very, very quickly without having to load it within the Redshift first. So they're able to produce reports delivered within seconds now. Very, very, very powerful example from one of our additional customers. So now we're going to shift over to a demonstration. And what we're going to demonstrate first is really how you could start leveraging Redshift Spectrum to extend that data lake and issue some of these queries, and how to set all this up. So we're going to start off here showing the Redshift cluster that we're going to connect to. So this is the Redshift cluster that I'm currently running that we're going to use in the demonstration. I just launched it a couple of weeks ago in order to do this demonstration. And what we can do here is I'm going to connect just through a JDBC connection. So I'm just using PostgreSQL here to connect into the Redshift cluster. And very easily what I could do is I could issue queries and see what's already loaded on this Redshift cluster. And we see various event data. So there's event, category, listing, users, venue, that sort of thing. We could very easily go in here and look at what does the event table look like, or what does the category table look like. And we see this is event data, so this has to do with venues and categories and sales and different information about events. Very easily what I could do is I could issue select statements here and start looking at, for example, what are the sorted by time, what are the first 10 events within the data set. And all this data was loaded out of S3, but it's already on the cluster. So we're not leveraging Redshift Spectrum Red. We're actually leveraging the data that's on the Redshift cluster. But let's start extending that cluster into our data lake. Let's start analyzing some additional data. What I could do is I could list all the schemas, and we notice there's a public schema that I'm querying over now, but there's also this transportation schema. This transportation schema is actually an external schema that Redshift Spectrum is providing that allows us to query the data as if it's a schema locally and join it with various data sets that we have here. If we want to look a little bit more into this schema, what we could see is there's a set of views here that allows you to really dive into the details of the configuration of the data catalog definition that's extending into S3. So here we can actually see the external schema, the IAM role that's going to be used to access that schema. This is a very important aspect when accessing the data within S3. It's leveraging an IAM role to do that. What we could also do is within that schema, though, we could actually look at what the tables are. So this is a Parquet table here, and remember this is a schema on read table. So we've defined this table out on S3. But the data could be stored first before we define the schema. And this happens to be Parquet data. And here we could see where the location is on S3 for that data set. In addition, what we could do is we could look at what the partition information looks like. I'm only going to print the first 15 partitions. But what we can see here is using this other view is all the different partition values. So if I query based on year, it's able to do partition elimination and only scan over the data sets within these prefix locations within S3 when I'm querying against this external table within Redshift Spectrum. What if I want to add another external schema into this? So right now, if we take a look, we see two schemas listed here. What if I wanted to add another one? So if I open up the Glue console here, you'll notice that I have a couple different databases defined. I have this transportation database defined, but I also have a data lake database defined with New York City taxi data in it. So if we go back over to the Redshift connection here, and we issue a query here to be able to create a new external schema, what we could do is we could start leveraging that definition in Glue. And we're going to do this during the demonstration. So I'm going to go ahead and create this external definition of the schema called data lake. And now if I go ahead and print the schemas, you'll notice there's a new schema listed here called data lake. Additionally, if I list the tables, you'll notice there's a new table that's shown called New York City taxi rides. And this was pulled from that Glue data catalog that I just showed a moment ago in within the console. We're going to start querying this data in a moment, but what if we have some additional data that we want to crawl? So if we take a look at this data lake definition, we only have one table defined in here now. What if we want to crawl another location in S3 and populate a lot more tables within here? So what we're going to do is we're going to crawl this data source here. This is an S3 location that I have many different data sets within. So what we're going to do now is we're going to go ahead and create a new crawler to be able to crawl that data source. So to do that, I'm going to go to crawlers and add new crawler. I'm going to just call this webinar and select next. And here we're going to specify the S3 location that we want to crawl. I'm going to crawl that location that I just showed a moment ago within the S3 console. I could have very easily specified a JDBC endpoint, for example, if I was crawling a relational database or crawling a data warehouse. All the crawlers always execute within an IAM role, so this IAM role is going to be leveraged in order to do the crawling. And then you can set up various frequencies and what database for it to populate. We're going to select the data lake database. So we just created a crawler during the demonstration, and we're going to run that crawler. And what this crawler is doing now is it's using those classifiers that we just talked about, scanning over based on that IAM role. So that IAM role is allowing you to set up least privilege permissions against S3. And it's looking through that S3 location to be able to understand what data you have. What are the different schemas? What are the different data sets? And what are the different data types across those schemas within there? So what we're going to do is we're going to switch back over to this table definition. And what you'll notice is there's a lot more tables that show up here, right? So in addition, I have it currently filtered by data lake still. In addition to that New York City taxi rides, we see a lot of different data sets ranging from Twitter data, IoT sensor data, and across the data catalog here. You'll also notice that it identified data format. So here we see JSON, CSV, Parquet as part of the crawling process. So let's take a look at some of what it discovered. So this is some of the Twitter data it recognized. It automatically identified it was JSON. And the crawlers actually identify a very nested object. So if I try to create the schema myself with all these different structs, it's not just one level of structs. If we take a look at one of these, this data actually has a structs of structs of structs of structs. So it's a very nested object that it automatically identified for me. So if I try to do this myself, I think I'd pull out all my hair and spend a couple days trying to get it just right. In addition to finding that complex data objects, it's able to identify the partitioning information. So if I bring up this IoT data, this is sensor data that I identified. This is JSON data as well. You'll also notice it identified there's actually 4 partitions of this data. It didn't identify the column type, but we could look at why that was. So if we take a look at the actual partitions and look at the view files here, Well, notice this data actually isn't stored in a Hive compliant format. So it's not actually storing the year equal, month equal, day equal, hour equal. So it doesn't know what the column names are within the crawling process. But what we could do here is we could go back to the table definition, and we could change it. So let's go ahead and edit the schema here. And we're going to actually just call this year and hit save. And we just created a new version of this schema, this table definition. And here we can see the different versions here. There's only two because we just created it a moment ago. We could also go in here and say compare versions, and we can see that the first partition was actually used to be called partition 0, and now it's called year. But if your data is formatted in a Hive compliant format, you'll notice that in this example, it found year, month, and type automatically, and I didn't have to go in and rename anything. I didn't have to go in and modify anything. It automatically identified it because it has that partition information inside the S3 objects. So let's go back to our Redshift connection here. And let's take a look at all the different tables Redshift knows about now within Redshift Spectrum. And when we issue this query again here, listing all the tables, you'll notice all the different tables are now showing up that we just found using the crawling process. So we see the New York City taxi data, but we also see that Twitter data and the sensor data and the other data sets that we just found during the crawling process, along with where they live on S3. We're going to start analyzing some of this data now. So let's go ahead and take a look at the partition information for the New York City taxi data. And the reason I want to show this is rather than this being partitioned by one value, the year, this is actually partitioned by the year, the month, and the type of taxi it was. New York City actually has different types of taxis, such as yellow taxis, green taxis, and for hire vehicles. I'm only showing the first 15 partitions, but there's hundreds of partitions within this data set. What we could do within here now, though, is we could start querying this data. So what I could do is I could actually start issuing, select statements, and this is querying based on the month and type. For 2016, what's the average distance and average cost per mile based on the different type of taxi? And you'll notice I issue a Redshift query against this data. I just specify the schema name and the table name, and Redshift and Redshift Spectrum do all the work of knowing how to scan the data out of S3 and return the data set back to me. I happen to be using a Postgres connection here, but this could very easily be a BI tool such as QuickSight and other BI partners that we have that integrate with Redshift and Redshift Spectrum. What I could do now, though, is I could actually start looking at this query. So let's get the query ID that this was. So this was 5651. And let's take a look at what Redshift Spectrum was doing under the covers when it was doing this query. So we could leverage some of these administration views to understand what was being done. So here, what we're looking at is for this particular query, how many files were scanned out of S3? What were the return bytes, return rows, and scanned rows out of the data set? This starts letting you understand how your queries are performing against your different data sets, your partitions. And we'll talk a little bit about the best practices and how to use these views after the demonstration here shortly. So this is a high-level detail of the query. Let's take a look at some of the additional information here. So what we could do is per slice, we could take a look at how the query was performed against Redshift Spectrum from each slice against the compute nodes. So each slice on the compute nodes actually issues queries down to the Spectrum layer. And here we can see each slice and each segment, how many files were scanned, how many objects were scanned, what return data set looked like. But what we could also do is we could actually start looking at if this information, if this query was effectively leveraging partitioning. So earlier we were talking about partitioning our data and using partition elimination to be able to eliminate scans against your data on S3. So what we could do here is we could leverage some additional queries here to be able to see how many total partitions are there in this database, in this table. There's 163 partitions. And you'll notice that we only had to scan over 36 partitions. And that's because we specified the year. And there's actually 3 different types of taxis and 12 months. So 3 times 12 is 36. So we only had to scan over 36 partitions when there's 163 partitions total. I should have mentioned this entire data set is about 3 billion entries. So it's about 8 years of data across the different data sets that we're querying over. What happens if I actually do another query here and I specify a slightly different year? I'm going to specify 2014. And the reason I want to show this is you'll notice there's only green and yellow taxis in this data set. And now if we actually look at the number of partitions scanned here, since there's only 2 data sets instead of 3, you'll notice there's actually 24 listed here because there's 2 data sets and 12 months in the year. So it's only scanning over 24 partitions in this example. So I wanted to show actually 2 examples there. One actually had 3 different types within it. The other had 2. And it's leveraging that partition elimination, knowing how many partitions to scan over the S3 prefixes when you're issuing those queries. So this is the data that's actually locally on the cluster that we're looking at now. So we're looking at category, events, listing, user data. If we take a look at the data that's actually on the Redshift definitions, we notice sales data. So there's this sales data that we may want to join with the existing data that's actually on the cluster itself. And we're going to do that next. So in addition to querying just the data that's on S3, what you could do is you could actually join occurrence the data that's locally on the cluster on the compute nodes. So this is a query that's going to be joining the event table locally with the sales table that's in our data lake and be able to pull back the top 10 events joining that data sets together. And you'll notice very easily, I issue my query, it's joining those data sets together, even though one data set's locally, the other data set's on S3, and returns the results back to me. And again, this could be done through various BI tools and other interfaces as well. We happen to be using this interface during the demonstration. What if I want to actually query some additional attributes across the 2 data sets? So in this example, we're actually pulling back the top 10 users, the top 20 buyers across these events. And this is fake data. This is fictitious data, but just to demonstrate the ability to be able to have your different data sets, dimensional data and other data sets on this in Redshift, but also extend those queries into your data lake when it makes sense to do that. One last query that I'll do here is actually doing a 99th percentile, bringing in the category data as well. And again, what you'll notice is I issue my query, very easily get the results back. It's pulling back the total price, the total sales out of the sales data that's on our data lake, but then joining it with the different dimensional data sets within the cluster, and it returns my data back to me very, very easily. So there, what we did is we demonstrated how you could very easily define external schemas within Redshift Spectrum to point to your data lake on S3, leverage Glue data catalog to be able to very easily crawl and manage that data catalog, and be able to issue these queries and really scale your Redshift cluster very, very easily. So next, what we're going to do is we're going to go back to the slide deck and start talking about some of the best practices when leveraging Redshift Spectrum and extending your data warehouse into your data lake. The first to talk about is the IAM callout. So Redshift Spectrum uses IAM roles to be able to allow Redshift Spectrum to be able to talk to your data on S3. We saw that when we did the describe schema call earlier using the view to be able to look at the schema definition of the Redshift Spectrum external schema. Next, we're going to talk about 5 best practices when leveraging Redshift Spectrum to be able to query your data lake. The first is if you have scan-intensive concurrent workloads. So what happens is when Redshift is issuing queries to Redshift Spectrum, it's delegating the work down to the Spectrum layer. So that frees up your Redshift cluster, your data warehouse, to be able to execute other queries. It also pushes down compute-intensive tasks to be able to do things like predicate filtering at the Redshift Spectrum layer. The other best practice is definitely leveraging column-oriented storage, such as Apache Parquet. What you could do is you could use 2 very good metrics to be able to see how your performance is being seen within your Redshift Spectrum. The first is the S3 scanned rows and the returned rows. You'll really notice a very, very good cost savings as well as performance increase when you're using column-oriented storage. What happens with that is when you're doing column-oriented storage, if you're selecting over a certain set of columns, it jumps directly to those columns when it's needed to do those queries. The third thing that you saw during the demonstration and a really good best practice is to partition your data. When you're partitioning your data, it's really good to partition based on various attributes that are queried on often. Oftentimes people will partition on year, month, those sorts of attributes within their data sets. Of course, you want very large objects within these Parquet files as well. One of the things that you saw during the demonstration is you could issue this query that you see on the screen now to be able to see how many partitions were leveraged within your query. That you can see if partition elimination is helping you for your various queries. The fourth recommendation I wanted to go over is really optimizing the queries to your data lake. So each Redshift node, each compute node actually has a certain number of queries that it issues per slice. And then each of those nodes actually has a limit as well. So you could scale your various cluster based on your different workload depending on your requirements. And the last one is to really focus on predicate pushdown. What that means is sending as much work down to the Redshift Spectrum layer as possible. So if your query does things like group bys, that could be done at the Redshift Spectrum layer, or like conditionals, count, sum, average, min, max. Those sorts of things could very easily be pushed down to the Redshift Spectrum layer, which helps with the distribution, the parallelism, as well as frees up your work for your Redshift cluster itself. Operations like distinct and order by need to be done globally, so those are still done at the Redshift layer. A really nice trick, you could actually do group by rather than distinct if you specify all the different group by attributes. And that improves certain queries, so that might be one thing worth looking at. There's a lot of really great resources out there on data lakes and data warehouses on AWS. There's the YouTube channel, there's best practices, there's our AWS Big Data blog. I wanted to do a call out on the Big Data white paper on building a data lake on AWS as another great resource that you could go to. So I hope this was helpful. I hope folks enjoyed the demonstration, and thank you for your time.